Hello and welcome. This is the part 2 of circular motion. In part 1, I talked about the basic definitions for the position vector, displacement vector, and the velocity and acceleration vectors for an object moving along a path such as this in the XY or XYZ plane. It could be three-dimensional as well. So what we have is, at any given point, of course, could define the tangential or tangent lines and the normal lines. Let's say these 2 points right there. This is the direction along the path. So I could take, let's use yellow. This will be the tangent here line, and perpendicular to it you will have the normal line here also. The normal line and the tangent line. Radial. Okay, so the thing is, the instantaneous velocity will always be parallel to the tangent line. So here will be your instantaneous velocity. Similarly, here along the tangent line. This is v, the instantaneous velocity. Well, in this picture, it looks like both of them look in the same point in the same direction. It doesn't have to be, right? I mean, v will change. So you're here, v will point that way, right? So v changes in direction, and in general, it may change in terms of magnitude as well, all right? Which is speed. So this quantity here, the magnitude of v is instantaneous speed. Now, if that instantaneous speed is not changing, if it's not changing, then the acceleration vector will be along the normal line. It's going to point in a direction which is dictated by the shape of the curve, which is downward here, and over here it's going to be this way, because it's curving that way, but it's along the normal line, because v is not changing in magnitude. But what if it's changing? All right, what if it's changing? Say it is increasing, then you will have it pointing this way. If it is decreasing, then it will point this way. Okay, so there are three possibilities in general for the acceleration vector. Slowing down, not changing speed, increasing speed. So let's say it's increasing its speed, and you have the acceleration vector pointing at a direction like that, while the velocity is such. Now you can always decompose this a vector into its components. A component along the normal line and another component along the tangential, on the tangent. All right, it's easy. Just like decomposing a vector into its x and y components, you can do the same for tangent and normal lines. So just draw a box around it, and then this will be the radial component, and this will be the tangential component. I hope you can see those colors. Anyways, so I could write A in terms of the tangential and radial components. A will be equal to AR plus A10. Now, today I'm going to derive a formula for AR. The magnitude of AR will be dictated by the shape of the curve and how fast the object will be moving. I don't have a formula for A10. Okay, I don't have it. But this, I'm going to show you how to derive the formula for that. Now, to do that, I'm going to use a model which will be the circular motion, a uniform circular motion. As you know, the position vector has a constant magnitude. Okay, so call this R0 and R. These are vectors, right? But both R and R0 are equal to capital R, which is the radius of the circle. And here I have delta R. Delta R, the displacement vector. Now, what about the velocities? Instantaneous velocities, which are perpendicular. Perpendicular to the position vectors. And for a uniform circular motion, these do not change in magnitude either. So I'm going to call this V naught and this one V. Both are perpendicular to the position vector. All right, that's our uniform circular motion there. Now, since along that circle, R remains constant, actually, I only need one variable to know where I am at a given time. And that will be the angle measured with respect to some arbitrary axis. Let's say this will be your axis here. Call it X, Y, Z, doesn't matter. But then you're going to measure the angle between your position vector and that axis. Call this theta 0. And then measure it again, call it theta. All right? So the difference between the two will be delta theta. Theta minus theta naught, which will be the angle between two R's. Delta theta. Okay, so what else do we know about a circle? Well, we know the circumference of a circle, right? 2 pi r. Everybody knows that, right? C equals 2 pi r, total length along the circle. But the object moves only from here to there in this time frame at arc length. let's give it a name. Let's call it delta S. Delta S. Delta S is nothing but the arc length that corresponds to delta theta. This arc length here. That's delta S. So let's write that down in terms of the angle. Now, if the total length is 2 pi r, and that corresponds to an angle 2 pi. 2 pi is 360 degrees, right? Now we have only a fraction of it, which is delta theta, but we still multiply it by r. Okay, so the ratio of this arc length to the total circumference will be equal to ratio of delta theta to 2 pi. That's what it means. All right, that's the arc length, delta S. Delta S. So again, the only variable that I need to know where I am on the circle is theta. That's the angular position variable, if you will. All right. And delta theta would be the angular displacement. Angular displacement. Okay. So it's measured in radians. Angular displacement in radians. So here's what I'm going to do. First, I'm going to find delta V. All right, delta V. So let me try to draw V again. Okay, so these are the R vectors, and these are the V, instantaneous V. Okay, but I'm going to take this and parallel transport it. Parallel transport it right there. All right, so these are V naught and V. Okay, and the difference is delta V. Just like I had a difference here, which was the displacement. So this will be delta V, whereas this is delta R. And I still have the arc length here, delta S. Right? That is delta S, that corresponds to an angular displacement of delta theta. Delta S is equal to delta theta times R. Now, what is this angle right there? What is this angle? How do we find that? Now, remember, this line here is obtained by carrying this line, the tangent, parallel. All right? It doesn't look like a tangent, but it is. But this line makes 90 degrees with this. So this is 90 degrees, which makes this angle here 90 minus delta theta. But I know this is also 90. So 90 minus delta theta plus 90 plus this angle that I'm looking for should add up to 180. Okay, so if you solve it for this, you'll find delta theta. Okay, so what you have here is actually two triangles which are similar. Okay, two triangles which are similar. First triangle, let's say it's this one, with sides equal to r and what is it, delta r. And another triangle right there, which share the same angle, this angle here, delta theta. Now, this comparison doesn't really make sense because one is velocity, one is position, but I'm just going to draw it like that. So this will be delta v, and this will be v. So is this side is v, okay? And the similar triangles have this ratio, v divided by r will be equal to delta v divided by delta r. All right, so that's good. Now, what if I look at this movement for a very small time interval? Okay, I talked about taking the limit the other day. So, limit when delta t goes to 0, which means really small delta theta, very small. Now, in that limit, delta r, which is normally shorter than delta s, becomes delta s. All right, so in that limit, I have here delta v divided by delta s. So here's what I'm going to do. I'm going to multiply both sides by delta s and r. So, no, let me just multiply by delta s. So v over r, this equation, and multiply both sides by delta s to get this. And I'm going to divide both sides by delta t. Now, the rate of change of velocity over time is acceleration. And the only acceleration we have here is the radial one, which will point to the center of the circle. Okay, so this guy here, if you carry it over there, somewhere in the middle, it will just point to the center. Okay, that's the centripetal acceleration. AC, which is AR. Radial acceleration is the centripetal acceleration. On the left-hand side, this quantity becomes the velocity, the speed, v. So we have two v's there. V times v is v squared divided by r. So this is the definition of your centripetal acceleration. Now I use this model here, but it's more general than that. So for these cases, AR will be equal to v squared over r. Okay? So the magnitude of the total acceleration will be equal to square root v squared over r squared plus a tangential squared. So it can be used for finding AR as well. It's not just limited to the circle. Okay, let me stop here.